Often the best way to prevent overfitting decision trees, however, is to use pruning, where you grow the tree to be much bigger than you need, and then you chop off parts that turn out to be less important. Now, pruning is very important if you're implementing a real-world decision tree algorithm. However, the details can get a little tedious, not too mathematical, but just a lot of little things you have to, a lot of T's to cross and I's to dot. And so we've made this section optional. You're welcome to watch it. Not a lot of math here, just a lot of detail. And so I would recommend you especially pay attention if you're implementing your own decision tree learning from scratch. But if not, just know that what pruning is, and we just talked about it, and know that most implementations, most great implementations out there would use some kind of pruning. We've discussed lots of recursions where you're building the decision tree from the top down. And we discussed two types of stopping conditions, the ones that we should always do, the stopping conditions from the previous module, and the 3 early stopping conditions from this module. Now, let's explore some of the challenges that come about with these early stopping conditions. Early stopping condition 1 was, let's pick a max depth and stop recursing once you reach that max depth. The question is, how do you really pick that max depth? We said you should use cross-validation or validation set, but there can be challenges with setting data aside for that. You have to rerun your algorithms many times, and you might not always reach the desired answer that you like, and plus you want some parts of the tree to grow more than others. It becomes really kind of complicated to set this parameter. Now, early stopping condition 2 is the most dangerous one. Early stopping condition 2 says stop if the training error stops decreasing. So if that classification error for the training data stops going down, so it flattens out. However, it turns out that in practice, the curve might not be as beautiful as what I drew. It might not be smoothly going down. It might jump and it might do some weird stuff. So let's see why that can come about. As we discussed, stopping condition 2, early stopping condition 2, stop when the error doesn't decrease, can be dangerous. And to show how it's dangerous, we need a counterexample. And we'll use the counterexample for everything, which if you saw the course 1, you know that it is XOR. So here's our data, and this data corresponds to the XOR of the first input and the second input. So when they're both false, the output is false. When one is false, the other is true, the output is true, which happens in the 2 middle rows here. And then when they're both true, the output is false. If you ever need to find the counterexample for anything, just say XOR. In fact, if somebody calls you in the middle of the night and asks, what is the counterexample for this crazy problem I'm having? You say XOR. So what happens with this XOR when we just look at the root of the decision tree? Well, we have 2 rows with output true and 2 rows with output false. And so what is the error of this decision tree, which just kind of top level? Well, you just choose one of these because they're all both the same. Let's say we choose true because we're optimists. We like to think positively. And so we're going to say that the output here is +1. And so that means that we're making 2 mistakes. 2 mistakes. So 2 out of 4 data points. So our error is 0.5. Which is bad. That means that you're as good as random. Just error 0.5. Okay, let's see what happens if we split on x1. Well, if we split on x1, and you're actually splitting the table like this, and you see that because XOR is so beautiful, we again, for each one of these subsequent nodes, we're in the same situation. So for example, for an x1 equals true, you have 1 y true and 1 y false. So let's suppose that you predict +1 for this side and also +1 for the side where x1 is false, because it's all even Stevens. So what's the error? Well, we made mistakes. No, mistakes were made. Mistakes are made here and here. So we made 1 + 1 mistakes, which is 2 out of 4. So it's 0.5. So it turns out that splitting on x1 does not help. Okay, Let's see what happens when you try to split on x2. So if I try to split on x2, I end up with the same situation, except I change this label here from x1 to x2. But again, we'll be in exactly the same situation where we're going to output 1 on each one of these outcomes and make the same number of mistakes. So 1 mistake for each, which gives me total error of 0.5. And so if I look, all in all, neither splitting on x1 nor x2 helps me reduce the error. So both splits give you the same error. So the question is, should I stop now? If neither feature improves and you're using early stopping condition 2, then you just say, nah, don't take any of those splits. You just stop splitting the decision tree at the very, very root. Output to be true, make 2 mistakes, and say that the error that you get in the end is 0.5. So this is why XOR is the counterexample to everything. What would have happened if you didn't take early stopping condition 2 and you just kept going? If you just kept going, you get this tree that looks here. And if you see, for each one of these leaves, there is 0 mistakes. So the leaf on the left outputs false or -1 and makes 0 mistakes. Next one makes 0 mistakes. The third one makes 0 mistakes. And the last one makes 0 mistakes. So if you kept going, if you didn't use early stopping condition 2, you would get training error of 0. And so in this case, there's a huge gap between training error of 0.5, which is as good as random, and training error of 0, which is perfect training error. So in this case, early stopping condition 2 created this arbitrarily large gap between the best thing you could have done and what you ended up outputting. So we saw early stopping condition 2. Don't stop recursing if the training error does not decrease enough. Seems like a reasonable heuristic, but it has some dangers, some pitfalls, because it's too short-sighted. It doesn't explore branches far enough. So it's kind of generally a good principle, but if you apply it top-down, you might get yourself into trouble. So what can you do about this? This is where pruning comes in. It uses something like this criterion, but it uses it bottom-up.